Colloquium. Professor Timoteo Carletti, better known as Theo by all of us, and who is going to give the colloquium. Theo is Italian, for those who like to speak Italian with him. Is Italian. He did his master in Florence and started also his PhD between Florence and Paris. And then he's been postdoc in Paris, also at IMPA in Rio de Janeiro, in Padova and other places. And from there he went to Belgium, where he has done essentially his career at the University of Namur, and where he nowadays he's full professor. He started the Namur Center for Complex Systems in 2010 at the University of Namur, which was later converted into the Namur Institute for Complex Systems, which is known as NACSYS. And he will now talk to us about Turing patterns on networks and beyond. Well.
Okay. Thank you very much. So thank you, Hilda, for the introduction. Thank you for the organizer to invite me today. And it's a pleasure to deliver this colloquium. So once Hilda invites me, I say, okay, accepted. Then I look what we are doing here at ICTP on physics, and I recognize things that I saw very long time ago when I was a student of physics, like string theory, field theory. So and I wrote to Hilda, but I'm not doing nothing of this. But you say not a problem, because here students are really open-minded, so they will appreciate whatever you are doing. So I did a selection of stuff, these Turing patterns. I don't know if you are aware of, but I hope at the end of the talk you will know what are Turing patterns. And then I work on Turing patterns on networks, and I will show what does it mean to go beyond networks. So I selected a few topics in this framework, and I hope that you enjoy this idea Turing pattern with the idea of applying this Turing pattern to other framework. So this is a list of students that I had in the past. I have now, starting from the master's student, PhD student. The star one are the ones that are nowadays working with me. Some postdocs, so Marcelo is here, and then a lot of collaborators that you already heard about also in the previous talk during this workshop. So the work that we present is based on a collaboration lasting more than 10 years, maybe 15 years with many of them. What I'm also very proud of, there are some guys that did all the jobs. So start from student, became PhD, postdoc, and then I have fixed position such as Marlborough Aslanich is in Florida State University, and Julien Petit, who is now in the Royal School in Belgium. So they really did all the path. And this proved that I'm quite old also, because I have a student that already have a job, a fixed position. Okay, so as asked by Hilda, I prepared a few slides about my short career. And so I didn't put my master thesis, which is in physics in Florence, and then I did my PhD in mathematics in between Florence and Paris, so Italy and France. And then I'm back in Italy doing some postdocs in Padova, again in France, and then again in Florence, in Pisa, in Venice. So I move back and forth between Italy and French. And I think quite a lot of Italian enjoyed this kind of movement across Europe. And now since 2005, I am in Namur. I started with a lecturer, then I became professor. Now I'm a full professor. I'm the head of the dynamical system team, and I've been director of NACSYS, and then I'm director of the math department since 3 years ago. So just to give you an idea of the scale, so this is the scale of my movement in Europe. So Florence, Paris, Florence, Pisa, Venice, Padua is here, and now Belgium. If you wonder what is this real scale, I just put my travel today, so you cannot ever see all my displacement inside Europe because of the very huge distance across the world. Okay, so this is my past, my career, and I'm interested in several stuff that are really related to this workshop, that is dynamical system, of course, on networks, and then higher order networks. It can be simple complexes or hypergraph. I will show you later on what does it mean. Turing pattern, this means that you have a reaction diffusion processes running on top of this structure, or you can be interested in synchronization, so you have a coupled oscillator, chaotic or regular one, that they do interact to synchronize, or in consensus problem that is more related to opinion dynamics, but again, is a sort of synchronization. Okay, so at the end, if you enjoy what I talk about, be aware that I got a grant from the Belgian government for 3 PhD grants starting from October and 2 postdoc grants for 2 years each, also starting from October, on this project, which is called Emotion, which is emergent motion in interconnected systems, where the math, the physics behind is a random walk, Turing and vertex models, so more statistical mechanics, and universal distribution of these random walks and Turing. And I just received yesterday or the day before this announcement from my university that there is this open call for collaboration between Brazil and Belgium, and I think that the deadline is mid-July, something like that. So if you're interested in one of those or both, please drop me an email. My email is here in the middle of my slides, and we can interact, have a chat, and so on. Okay, so let me start now with the talk, the colloquium. So the starting point of my interest, of my research, is observation that order is emerge from disorder once you look around us. So that was I mean this. So if you look at this is a cauliflower, this is an animal, a fish, and so on, you can observe that on the skin of these animals, you have some regular, more or less regular structure called a pattern of motif. But if you look at the microscopic level, this motif are the result of interaction of chemicals, say, that normally interact in some nonlinear way. And so once you have a nonlinear dynamics, maybe in even higher dimension, you do not expect to see regular stuff. You expect some chaotic behavior or in some non-regular one. So the question is, how is it possible that you can observe such a regular structure emerging naturally or spontaneously without any control from microscopic rules that are non-linear, that involve huge number of agents or species or chemicals. And these kind of patterns can be seen in the animals, can be seen in a chemical reaction. So here you have a plate where you put some reactant, and then you can have this spot-like, this labyrinth-like that spontaneously emerge because of the reaction of the chemicals inside the dish. Or you can have social patterns. Each dot here is a student of a primary school in France, and the color represented the schools. And they did an experiment. It was like that. They put a RFID tag on each student, so just like this one, but with a communicator, a sensor. And then each time the two tags are close enough, 1 meter, then they say, okay, I'm Theo, you are you, and we are discussing. And so in this way, they reconstruct, maybe you cannot see, but there are links. They reconstruct the links among the students. And then you can recognize, of course, a lot of links inside each class, but also links across classes. This means that during the playground or during the lunchtime, the students interact. So this is the standard idea. Then you can run on this kind of data some epidemics model, some opinion dynamics model. So this again, you have the emergence of this structure just because the interaction of these many students in France. Or at the end, we will see this kind of patterns that are, say, mathematical pattern, or which is this, you have a network where you have some dynamics on top of each nodes, the nodes interact, then at the end you will have some nodes that will not change their amount, so they're very close to zero, very slow, and some high node with a very high amount of some quantity that is diffusing or produced on this network. Okay, and so this idea of order from disorder has been very well explained by Murray in this. This is a page of a paper, but he has several books about, and that is how leopard gets his spots. This is the idea of how coats of animals exhibit this kind of patterns. Here I just copied some example or tails of different kind of animals. And one of the interesting results is that you can have, so these are the mathematical theory if you want. So you can have this kind of spots or this kind of or dots, this kind of stripe, but you can have ever a stripe that is along the tails. So you cannot have an animal that are the stripes in that way. So this is a mathematical proof, and indeed, we don't know any animals that has this kind of tails with a line in the same direction of the stripes. Okay, so one possible mechanism to explain the emergence of this kind of patterns has been proposed by Alan Turing, the same Alan Turing of the universal machine, the Enigma, the cryptography, or for those that attended yesterday the talk by Tiago Pereira, is the same Turing that he described yesterday. The idea of Turing is the following, or was the following: in the 52s, so at the end almost of his life, he wrote this paper, Chemical Basis of Morphogenesis. Morphogenesis means the birth, creation of shapes, of embryo in some sense. So how animals are formed starting from few cells. Okay? The idea of Alan Turing was the following. Consider, I will speak about chemicals, but can be any interacting agent in some sense. So assume to have two chemicals that interact each other. So if for a moment remove space, they are stuck in some position. Or if you want, they are well mixed inside some space. Then once you have these chemicals, you have the back reaction, the fourth reaction, and normally using by mass action, the chemical that has the higher reaction dynamics will win. At the end, you will have a uniform solution, say one color, which is the one which is the fastest one, okay? Of course, you can play on the temperature, you can play on the pressure, and change the equilibrium. But at the end, in principle, you expect to have one solution that wins. Now, assume that you can switch off the interactions of the chemicals, but they can only move around, so they can diffuse. Again, as been said yesterday, if things diffuse, at the end you expect a uniform distribution. If you have something that diffuses here, at some point it will be in all the room. Okay? And so the idea of Turing was the following. What happened if I had together this reaction and this diffusion? Now the chemicals can locally react when they are close by, but then they can move around. Okay? And so the idea of Turing is the following. You take this scheme, so reaction inhibitor. So this means that the yellow species is capable to create itself, but also help the other species to be created, while the inhibitor one does the contrary. So that the inhibitor prevents the yellow from growing in some sense. Okay? So if you want to model in a continuous framework, you have some domain, that here I call omega, and you have some reaction term f and g, normally some nonlinear reaction function, and then you have the two diffusion coefficient, the u and the v, and you have some kind of diffusion, so a second order derivative. Okay? So the question for you, for the student, not for those that attended yesterday the lecture, what you expect from this? You have two homogenizing mechanisms, one because of the reaction and one because of the diffusion. You put together, what do you expect? Do you expect homogenization or something different? Okay, it's not a lecture, it's not an exam, so you can, there is not market. Sorry? But so at the end, you will have everything homogenized, the faster will win. Okay, another possibility? No? More? No? Okay, so no, it's the contrary. Once you have diffusion and reaction, so two homogenizing stuff, at the end you can have a patchy solution, a heterogeneous solution. And this is true, the faster one will win, but normally the faster one should be the inhibitor, so this will be proved in the end. So this means that the inhibitor will go faster, will kill almost everything, but where the activator will remain, it will be able to produce itself. And this will create a patchy distribution of chemicals in this case. And this is why the Turing patterns are called diffusion-driven, because if you remove the diffusion, you will not have any heterogeneous structure, but because of the diffusion, you have the creation of this patchy spatially solution. Okay, so this is a first order steps, and then so then the nonlinear terms will saturate, and you have a constant distribution. Yeah.
to understand. So U and V are what? U and V is one
So
of the color and V is the other?
U and V is the concentration of some chemicals in space. So U is a function of X and Y space.
So when you
T
say
time.
patch, I think of some patch is just U and some patch is just V. I don't
No,
know what you mean by patch.
So here I'm assuming I'm working on a continuous, so
Yes.
it's in some plate. And then you have the position is X and Y. U is the density of some chemicals in this position at that time. V is the concentration at the same point, in some sense, at the same time. So this quantity U and V can diffuse because they can move and they also interact.
But for some reason you don't, U and V are somehow exclusive. You either have only, you say patch, so patch means you have some patch where
No,
it's U
sorry,
and
I use the
says
word
V.
patch to mean that at the end you have heterogeneous distribution. So at the end you will have here, there are all the V, here all the U, here all the V. So they distribute themselves automatically if you want.
So why do they exclude? Why don't you have something like half U and half V?
Sorry?
What I don't understand is why you have a patch where U is the main ingredient and another patch where V is the main ingredient. Why don't you have things which are half U and half V?
Okay, so I'm sorry, maybe I used the wrong way. The wrong word is not patch. So U is a density.
Yeah.
So it's not alpha U. U is at 0.5. V, okay, so in that point, you can have U equal 0.5 and V 0.9. But then these react locally, but they also move around. So maybe at the end, here we will have U equal to 0 and V equal to 1. But if you look nearby, you have U equal to 1 and V equal to 0. So the region where V is maximal or U is maximal, I call this a patch. Indeed
But there's no, sorry, just to ask these questions. Is there a constraint that U plus V has to equal to 1 or something?
No, because you have the reaction. So U and V can increase.
Be any values.
Any value. But as I say, because of the nonlinearity, at the end, they will saturate. You can have
any nonlinearity, they separate? I just don't understand what the...
No, there will be some condition on F and V. So here I'm just, F and G, sorry. Here I'm just discussing the general framework.
And the condition is that somehow it likes to be either just U or just V. That's the part that I don't see coming out of this equation.
No, of course, you cannot see from there. I will show you why this is the point. Okay? Okay, so if you have a question, do not hesitate to interrupt me. Okay, so this was the classical framework of Turing, so more than 60, 70 years ago. Now I will speak about networks. Okay, I will not insist too much because we are almost all aware of what the network is. I just put some figure. So again, one example of network is the world flight maps, where each nodes is an airport, and two airports are connected if there is a connection flight. And then you have here all the connection among Europe, US, and the rest of the world. You can have a network where the nodes are the protein, and two proteins interact. So I draw a link if they are able to interact to produce a third protein or something else. Or you have the social networks, of course, where you have a different kind of framework where people can exchange images, messages, opinion, and so on. And then you have also some real networks. What I mean real in the sense of wired. Here, the links is really a cable that pass from one plant to another plant. And so you have some technological networks. Okay, so network is very general framework where you can model a lot of different stuff. You already saw during this workshop other example of network, so I will not insist too much on network. Okay, but just to fix the notation, a network is nothing but a set of nodes, say the basic unit, that are connected by some links because they in some way interact. They exchange some information. So this is a small network made by 5 nodes, 1, 2, 3, 4, 5. There are some links, and you can count how many links are connected to node 1. There are 3, and this is called the degree of node 1. 5 are degree 0 because nobody is connected to 5. 3 are degree 1 because 1 and 3 are only connected among them. And then you can use this matrix that you already saw during this workshop, which is called the adjacency matrix, Aij, which is 1 if node I and j are connected, and 0 otherwise. Of course, you can use weight, you can use directionality. There are several variations, but this is really the basic idea. And normally, we say that a network is complex if the degree distribution, so the probability to have some node with some given degree is not a trivial, in the sense trivial is a lattice where everybody has the same distribution, or is not a Erdős-Renyi, so a random one, even if sometimes Erdős-Renyi networks can also be put in the class of complex networks. So in general, you will see a scale-free, small world one, but just some name, few names. Okay, the second point is that on each node, here network are not, so each node is not an individual, like in the social network where each node, so I'm a node, I'm on Twitter, so I'm a node on Twitter, and when I retweet or send a tweet, I make a connection with some other person. So this is a case where one node, one person. Here is different. Here one node is a spatial distribution of space, or real space, where several agents can be together. So what I'm using here is more this metapopulation model that has been introduced by Robert May times ago to explain the emergence of order or disorder in the ecological landscape. So you have a patch here, so a node where several animals in the framework of May, they will interact via some locked Volterra, but also animals can move from one patch to the other patch of the forest or whatever, okay? So you can think that in each node you have, if you look with a zoom, you have a lot of particles that move around and interact. So in each node you have a sort of mean field, so you can describe the dynamic inside the node with some differential equation, and then you have interaction, and the way you model the interaction will depend on what you are interested in. Okay, so as I'm just saying, in each node now, so now space is discrete. Space is the number of nodes I, 1, 2, 3, up to n. So the concentration of U and V at time t on node I is given by some function that only involve U and V and node I, because they only react locally inside the patch where they are. Okay? So this is the metapopulation about the discussion. And this idea has been extended by Nakao and Mikhailov 10 years ago, 15 years ago almost, to study Turing pattern on networks. Okay, so now I will briefly describe the theory by Nakao and Mikhailov. So the second point now is the diffusion. And so the diffusion, I will use again my example of network. So if you want to understand how the quantity in one will evolve if you remove the reaction but only take into account the diffusion, then you can say, okay, one receives some quantity by 2, by 4, and by 3. So the evolution of U1 is the sum of what is incoming minus the sum of what is outgoing. Okay? So if you write this equation by using the adjacency matrix, you see that the variation in U1 is given by this sum minus the degree, because 3 is the number of neighborhood of 1. And then you end up with this equation where I just use this fake delta symbol because I want to fix I, say j equal to 1, so I write this one. And then I have this matrix, Lij, which is called the Laplace matrix of the network. It's called Laplace matrix because if the network were a lattice, this is exact the second order derivative discretized. Okay? So then if your network is not a lattice, we keep the same name and we use this name of Laplace matrix. And this idea of the evolution of the quantity in I be related by what I receive minus what I can send to the other, yes, it's a sort of Fick law. I try to homogenize my quantity with respect to what I have in my neighboring one. Okay? And so if I put everything together, this is the scheme that now we have in each node, then you have the reaction part in node I, so only involving UI and VI, and then a diffusion that is multiplied by some coefficient, so the diffusion coefficient of species U and V, and now we can observe that instead of second order partial derivative equation, you have an ODE, so an ordinary differential equation, so much easier to be studied than the PDEs. Okay, and so now what I will show you is how you can, from this equation, prove the emergence of patterns, so this distribution of quantity UI and VI that are segregated across nodes. Just one remark, so this is function Aij is symmetric if the network is not directed, is undirected, is the assumption that I will use for now. And so the matrix L is also symmetric because it's the matrix I minus a diagonal matrix. Okay, so I will deal with two symmetric matrices. This will be useful in the following. Okay, so just to show you a short movie. So here I show you the Brusselator model. So I assume that in each node, okay, sorry, this the X and Y here should be not there. So okay, so yeah, so I assume that in each node you have this kind of reaction. This is a model that's been introduced by Prigogine and the people in Brussels the last century to study some generic nonlinear models. One can prove that he has a stable fixed point, and then there is an op bifurcation, so you can have a lot of very interesting behavior in this Brusselator model. But of course, what I'm showing you is valid for many other models, not just from the Brusselator. And this is the picture that I showed you at the beginning. I can put again, where I draw the network in such a way the nodes with a higher degree, so the node that have more friends, more neighborhood, are in the center, and node with a lower degree on the periphery of my picture. Okay, so a network, there is no geometry. I can put the nodes wherever I want, but here I choose this kind of special description, and then you can see that you have accumulation of patterns inside the center. So the hubs, so the nodes with a higher number of neighborhood, they will have a higher amount of X. So here, naturally, you have a node where there is no V, sorry, there is no, I call here X, sorry, there is no X at all. And then if I had drawn the same for the Y variable, you will have a lot of V in the other. And then you have a node where you have a lot of X, U, and not the other. So they automatically separate into groups, going to high degree and low degree nodes. Okay? So my goal now is to explain how this is possible, which is the theory behind this. Okay? So the starting point is that, of the Turing theory, is to assume that your system admits this homogeneous equilibrium, which is the equilibrium given by reaction term without the diffusion. Okay? So you assume that your system admits this equilibrium, and then you can prove, because maybe I didn't stress enough, but the Laplace matrix is such that when you make the product with the vector with all the ones, give you 0. Okay? And this ensures that this solution, all the xi, all the ui equal u hat, and all the vi equal v hat. So this is the solution for the isolated system, is also a solution for the coupled system. I only write the one for u, because here, once you put in this equation all the u equal to u hat, all the v, all the v equal v hat, here this is a constant, then you are summing L over J, but the sum of all the L over all the J is 0, so this term vanishes once you have all the u equal, and then at the end you are proving that the solution u hat satisfies the equation u hat dot equal f u hat v hat. Okay? So the solution that you have for each isolated system is also a solution for the coupled system. Okay? Because otherwise, if it is not a solution, you cannot speak of existence of this solution. Once you have the fact that this solution is also a solution for the global system, you are interested to study its stability, because you would like to prove that it is stable, because this means that if you start close to this solution, then you will go to this solution. But because I want to prove that I will have Turing patterns, so I will not converge to homogeneous equilibrium, but I will go away, I have to prove that this solution will be unstable. And it will be destabilized by the reaction, by the diffusion part. Okay? So what we can do, because I'm interested in first-order approximation, I will write each variable ui as a perturbation about the equilibrium, and the same for v. And then I linearize my system, where the matrix J is this matrix, it's a huge matrix, because you have here the matrix L, which has the size of the network. So this is a matrix that has the size n times m, where n is the size of the network. And f, u, and so on are the derivative of the reaction part with respect to u and v evaluated on the equilibrium, this u hat equilibrium. Okay? And then what I have to prove, you have to prove that there are some conditions on the u and the v such that this solution is unstable. This means that if I start even closer as much as I want to this solution, because of the diffusion, I will go away from this solution, then I will go the system will converge toward another solution that maybe will depend on space, on node I. Okay, to do this, I just briefly show how you can do it. So this Laplace matrix, remember, is symmetric. So it admits an orthonormal basis that I call phi alpha, so eigenvectors and eigenvalues. They are so normalized to be orthonormal. Okay, and because of the definition I choose of L, the spectrum is real because it's symmetric and negative except for one eigenvalue which is 0 if the network is connected. This is the assumption that I use. So pay attention that someone in the literature you can find L defined with the minus, and then you have the spectrum is real and positive. So just pay attention on the definition. The idea is that now instead of studying this huge system whose size is very huge because it depends on the size of your network, and check if the spectrum of this huge matrix has a real, negative real part, I will try to simplify the problem by projecting my perturbation delta ui and delta vi on this eigenbasis. Okay, so I'll do this ansatz. I project and I assume that the time evolution of the perturbation on short time scale is some exponential with some lambda alpha. Okay, so to compute this lambda alpha, you have just to insert this equation, this ansatz in the equation, and you end up to solve this characteristic equation that is called whose root lambda alpha is called dispersion relation. So the idea is now to prove that this lambda alpha, I have to prove that there exists alpha such that some lambda alpha has a real part positive. Because if you have a linear system and you have some eigenvalues that are on the right part of the spectrum, then the equilibrium is unstable, and so the equilibrium, the solution will go away. And this lambda alpha will depend on the reaction part, but also on the diffusivity and on the spectrum. So what is important here, this now is a 2 by 2 matrix. It's not any longer an n by n matrix, because I compacted all the information about the network into a single number, lambda alpha, the eigenvalues. Okay? So this is really the important step that Nakao and Mikhailov did in the past. And so what I show here, I just draw this lambda alpha as a function of capital lambda alpha. Sorry for the lambdas, but this is the traditional calling that way. So the function, I show you the real part of this lambda, small lambdas, as a function of this parameter that are eigenvalues of the Laplace matrix. And then you add the dots, and you can see there are a lot of alphas for which this quantity is positive. So if I run this system, I expect to have the emergence of Turing pattern. While here, all the points are below 0, because 0 is here. And so if I run this system, I will not expect to have a Turing pattern, but everything will go away again to the equilibrium. Of course, this is a first order, so a linear approximation. So if I start far away from the equilibrium, maybe in this case I can also have patterns. But this is the difference between a linear approximation and nonlinear studies. Okay, so here I do the example. So I take again the Brusselator, my preferred system. He has this solution 1 and b over c. I compute the dispersion relation again as the previously, and I saw that there is quite a lot of points where the real part is positive. So I expect to have emergence of pattern. And again, if I look to this is the network, you will see that you have a concentration of large values of ui in nodes that again are the node with the largest degrees. So if you compute the degrees 1, 2, 3, 4, 5, 6, 7, and this is 1, 2, 3, 4, 5, 5 again. So the node with the higher degree will have a concentration, larger concentration of u, which is the activator, while the other will have a higher concentration of inhibitor. And this is just a plot, a time plot where you have sorry, so this time is not nodes. So you have nodes at times. You start initially from close to 1, you perturb, you cannot see the perturbation on the scale, and then you have the accumulation of u at some given node that are the same node over here. Okay? Any question? So this is really, yeah?
Sorry, what are the capital numbers in the previous slide?
Yeah, this one. They are eigenvalues of the Laplace matrix. Okay? This is because of the ansatz that I did here. So once you do the ansatz, you project on the basis, and you put this information into your linear system. Here you recognize that L times the eigenvectors gives you the eigenvalues times the eigenvector. It's just a computation, but if you want, we can do it. So
Small lambda is the Lyapunov exponent. Like
Yeah, this is Lyapunov
a
exponent, if you want.
Lyapunov
Yeah, it's
exponent.
exactly
So
the
real
Lyapunov
part
exponent of the
Lyapunov
equilibrium.
exponent.
Yeah.
I see.
Yeah.
So eventually it finds some stable pattern? I don't see that. What happens when t gets large? It
Okay,
becomes
so here, so this is a first order theory, so I cannot predict neither the shape, neither if it's stationary at all. I just say that if I start close enough to the equilibrium, then I will go away. Where, I don't know. This depends on the nonlinear part.
I understand, but then why do you call it the Turing pattern?
This is because it's the same mechanism that happened on a flat surface is happening on network.
So Turing pattern just means something goes out of equilibrium? I
Yeah.
just don't know what that's
Yeah,
all it
Turing
means.
instability is a bifurcation where a stable point becomes unstable because of the diffusion.
Okay, thanks.
Other question? No? Okay, so this was the theory of Turing pattern in the case of symmetric network. It has been extended to asymmetric network. The difference is that now the spectrum is no longer real, but is complex. And now what I showed you previously, this plot in 2 dimensions with the lambda and a small lambda, I cannot do anymore, but I have to work in the plane. And in the plane, so this is the real part of the Laplace spectrum, and the imaginary part, you have a region, this bluish region, that is if the eigenvalues are there, then the system is unstable, while if in the white region, the system is stable. So here is just, if you want, a section of this plot where you can see that the blue have a lot of points here, at the point for which the Lyapunov exponent, as you tell, is positive. The red one also, but the other are all below. So you cannot have a pattern on this directed network. And here is what you see. Here you have it's not stationary at all, they are waves. They are Turing waves, so propagating waves. Again, propagating across nodes, so you don't have a geometric structure underlined, but they are still called Turing waves in some sense. Okay. So in the previous slide, I had a symmetric Laplace, so there is a basis. Here in this paper, they studied the non-symmetric one, but still they assume the existence of a basis. With a student of mine, we just proved recently that the same holds true also if there is no basis. So if you have degenerate eigenvalues with multiplicity larger than 1, the same result holds true. For instance, you have a network made by 10 nodes, but once I draw the relation dispersion, I only have 4 points because I only have 4 different eigenvalues. Okay, but it doesn't matter. You can do the same. You can prove that just by using these 4 existing eigenvalues, you can prove the existence of Turing pattern. Here, what is interesting is that the generalized eigenvalues can, in some sense, predict the shape of the pattern. So here you can have some information about close bifurcation where the system will go once perturbed. So here the generalized eigenvalues can give you some information. Okay, so by recap, this is the Turing mechanism, which is diffusion driven. It's very simple, first of all. It works in several cases, but if you want really to have a real model that satisfies this equation, is a bit tough. There are examples, so experiments where they have Turing pattern, but there are several points. First of all, okay, you need at least 2 species, but okay, this is a minimum. What is important, you need activator and inhibitor. You cannot have inhibitor system. You will not have a Turing pattern, but most importantly, the inhibitor should diffuse much faster. So I didn't show you the relation, but behind the study of this dispersal relation, these conditions should be satisfied. Last point, you have PDEs, if you look, because you have the second order derivative. So in some sense, you have infinite speed of propagation, which is not physical at all. So we can try to capture some of this point, and I will show you something that can be done. Okay, so the first step that one can do is to use, instead of network, multiplex network. We saw this morning, we saw last days. And the idea is that now you have several layers, and you can have diffusion in one layer, diffusion in other layers, but also diffusion across layers. And what one can do here is write exactly the same system that I showed before. So this is the interaction in each layer. So assume you have k layers, but they are interaction across layers. Okay? And what I'm interested here is to study what happens if I move this possibility to switch from one layer to the other. So if the layer is disconnected, I have something. Once I connect the layer, I can have another pattern emerging. So this is, so I skip the math because it's exactly as before. You find the solution, you linearize, you end up with huge metrics that now take into account these I terms as been shown this morning because of the identity of the same nodes in several layers. You compute the largest the real part, the largest eigenvalue. Here you can use some perturbative approach because I'm assuming that the diffusion interlayer is small, and then you can end up with some result. I just show you the movies. Here I start with a system that once the network, the two layers are disconnected because I put dV equal to 0, so this is the example, then you will not have pattern. Indeed, if I run my system, everything goes to equilibrium. So I start close to equilibrium, I run the system because the relation dispersion is negative, everything goes to the equilibrium. Here, I increase the interaction across the two layers, and then at some point, this lambda max becomes positive. So the dots are the experiment, the line are the first order and second order approximation, quite good. And I can show that if you take dV sufficiently large, here for instance, this is the plot, now you have emergence of patterns. So you start again close to the equilibrium, you wait a bit, and at some point, the point goes away. I cannot predict where they will go, but for sure they will not remain close to the initial points. And then I will have this kind of pattern where you have nodes with high concentration and lower concentration of U and V. Okay, you can do the opposite. So you can have a network that one disconnected have patterns, and one they are coupled, they do not have. I will skip this part because it's exactly the same. And then I will discuss another point. So up to now, I consider the network is fixed once for all. But in many applications, networks do evolve in time because people will move or some links will evolve in time because of some reason. And so this the framework of a temporal network has been recently studied. And so I will show you what we can do for Turing pattern temporal network. The first result that we got with some colleague of mine is considered a fast switching. So this is an example. You have 6 nodes, and each time step, only 2 nodes are connected. Okay? So it's really a game that we play on your children, that you pass something just one or your friends. If you take any of these fixed snapshot, you cannot have patterns because the spectrum is these stars. And you can see that the stars are below 0, so you cannot have patterns on any fixed configuration. But if you switch fast enough among the configuration, you can use some theorem, it is called average theorem, to prove that there is some effective network, which is this network where links now are weighted according to the time that the fraction of time that this link is active with respect to the other, whose spectrum is positive. And so once you look to the pattern, you can see that there is this emergence of pattern. Of course, the patterns are not regular because of this switching. So this is a switch system. It's not irregular at all. Okay? But if you have fast switch, you can create pattern. But you can also create pattern without the fast switch assumption. You can take now any Laplace matrix that depends on time, slowly or fast, it doesn't matter. But you assume that is always a symmetric matrix, so there is an orthonormal basis or eigenvectors and values that now depends on time, and they are still orthogonal for all t. Then you are interested in studying how the eigenvectors evolve in time in the fixed basis. And once you do this, you do again, they assume the existence of the equilibrium. You linearize and blah, blah, blah. And you project. At the end, you find the same equation as before. So the reaction part plus the spectrum times the coupling. But now there is an extra term that tells you how the eigenvector varies with respect to the given basis. And these terms can create or destroy patterns. So this is a simple example. We have a network with 3 nodes, 3 links, and the links oscillating times with this very regular shape, continuous functions. Just an example. Okay. And so on this network, you can prove that this is the plane BC where I use my parameters for the Brusselator. The black region is the region for which I have Turing pattern, and the white one for which I don't have Turing pattern. So if I fix omega, so the network is static, it's not evolving, and I pick these 2 points, both give me Turing patterns because I'm in the region where the Laplace exponent is positive. But if now take omega equal to 2, so my network is is slowly evolving, this region, black region, shrinks. And then you can see that the point that previously gave me patterns now goes to equilibrium. So this is an example where the time-varying network reduces the possibility to have Turing patterns. Okay? Okay, I have 10 minutes maybe, yeah? Okay, so I will now pass to the second part, to the beyond part, which is, so we studied network, symmetric, asymmetric, static, time varying, multiplex, and now I'm interested in beyond network. Beyond network means that in the network theory, the main limitation is that nodes interact pairwise. So I'm interacting with you, but separately. But in many interactions, in real social life, you have many body interactions. So being a triangle is not being as the sum of three links. For instance, if you have a paper that has been written by 3 authors, it's not as the same as 3 papers pairwise written. It's something more in the group in some sense, okay? And so the idea is to see what we can do in this framework for Turing pattern. So here, I heard the theory or framework divides in 2 main groups, simplicial complexes and a hypergraph. I think I will skip the hypergraph part. I will go direct to the simplicial complexes because I don't have time. I think I spent too much. So, okay, I skip the hypergraph. Sorry for this. But you can prove the existence of Turing pattern on hypergraph. But so I will present simplicial complexes. So simplicial complexes are nothing but, again, network, but where now nodes are connected not just by links, but are connected also in triangles, where I mean that now the triangles is part of my structure. But you can connect also by using 4 nodes, and so you have tetrahedra. Or you have 5 nodes. I cannot draw the picture, okay? So simplicial complexes are structures that are built by using basic blocks, triangles, tetrahedra, 5 vertex solids, and so on, okay? And in this paper, we studied the emergence of Turing pattern in the case of a network that is formed only by links and triangles. Okay, this kind of links. But again, here we assume that the dynamics is on each node. So on each node, I put some Brusselator model, or whatever you want, and then you take into account that you have pairwise connection, so in some sense diffusion-like pairwise, but also you have this kind of 3-body interaction. There are these terms where you have this tensor here that tells you how many nodes are acting together, okay? So in the case only triangles, links, and nodes, you end up with, again, assuming that it is equilibrium, you perturb, you end up with this new equation, which is this part is the same as before, but now you have a new Laplace metric, which is Laplace that tells you how triangles are connected among them, in some sense, or through links. And the point is that now you cannot use the same trick as before of using the basis of L1, because maybe in this basis, L1 is diagonal, but L2 is not diagonal at all. So you cannot simplify the equation, and then you need extra assumption or on the L, so on the structure of the simplex, or on the coupling, on the JH1 and JH2. So you can do the theory, but you have some constraint that you have to respect. Okay, so up to now, I used the many-body interaction just to say, okay, these 3 points do interact, and I take into account by the fact that you have some function h that depends on 3 variables at the same time. But one can do something more, and what something more is the following, is the idea of topological signal. So you can think that, okay, I have a system evolving on a node, but maybe there is also a system evolving on a link, a current flowing across 2 nodes. But maybe there is also a system evolving on the face of the triangle, some magnetic field which is circulating. And the current will interact with the nodes, but can also interact with the circulating magnetic field, and vice versa. The magnetic field can interact with the links. Okay? So you can have a signal that live on nodes, links, triangles, tetrahedra, and so on. And we call this signal topological signal because they depends on the topology of the simplicial complex. So what I will show you in the last few minutes is how you can extend the theory by Nakao and Mikhailov of Turing pattern from networks to simplicial complexes. Okay, so just to fix the notation, because I'm not sure everybody is aware of what a simplicial complex is. So again, I say it's a triangle, but what is very useful here is that you have to choose an orientation. So pay attention, orient a simplicial complex, it does not mean that it's directed. It's just a fixed labeling, okay? Because a simplicial complex, I like to see as triangles, but it's also a topological object where you put the index of the nodes. So if the nodes are 1, 2, 3, this is just a triplet 1, 2, 3. So I can work on this level of algebra. I don't need really the geometry, okay? But because the geometry is very useful for the topology, it's useful to orient the simplicial complex. And the orientation is, for instance, you can think that you orient according to the labels. So you say 1, 2, 3. So in this case, I just use this one. So yeah, 1, 2, 3. So you say because 1 is more than 2, I put an arrow going from 1 to 2. Because 1 is more than 3, I put an arrow going from 1 to 3. And because 2 is more than 3, I put an arrow in that way. Okay? Of course, I could have chosen another orientation, but this is just a change of basis. So in because the simplex is a finite object, you can see as an object living in some vector space, and so changing the orientation is just changing the basis. And this is interesting because if you take one links, and you say, okay, I orient in that way, but on these links there is a physical current that go from right to left, left to right. So this means that this current has a sign plus because it's the same orientation. But if I decide to change the orientation, but of course, the physical current will not change because this is a physical. This means the same current will have a minus now. Okay, it's like once you change the orientation of your space. And so this is important because they will change something in the dynamics, but will not change the result at the end. Okay? So once you have oriented the links, you can also orient the triangles. And so once again, I can use the orientation that takes the labels in the increasing order. So I'll say that this triangle is oriented in that way, 1, 2, 3. Okay? And then what I have to do is to write this matrices B that tells me how the links are connected to the triangle if they are organized in the same way, if they're aligned in the same way. So if you look here, these arrows are rotating the way, so out from the blackboard, and 1, 2 is going from left to right, so they are oriented in the same way. That's why when I write, so this is the first one, so it is a plus here. So the link that is 1, 2 in my blackboard is oriented in the same way the triangle. Link 2, same way, but the link 1, 3 is oriented in the opposite way because the arrows is going that direction while the link is going upward. And so that's why I have a minus here. I can do the same with the nodes and the links. And then indeed in these matrices that are called incidence matrix, this is all the structure of the simplicial complex. So I put everything in some geometry or algebra if you want. Once you have these matrices, okay, you can do for, I did here for triangle and links, but you can do for tetrahedra, whatever you want. What you can find is this matrix called L, which is the Laplace, the Hodge Laplace matrix, which is generalized the Laplace that we saw in the case of the network, which is the case k equal to 0. 0 is nodes, so this term disappears, so you only have the standard Laplace matrix. Okay, and now so what I have my U, which lives on nodes, for instance, V on links, and then you have some reaction that takes into account the quantity U on the node. B1V tells me the quantity that is flowing through the links 1, 2, but evaluated in 1 and 2. So these terms here is a local term, is what is happening in node U. And here I have the opposite part, so you have G that depends on the current flowing on the link, but times or with some function of B1 transpose that tells me the difference is some sort of gradient, the difference of the amount of U in 1 and 2. Okay? And then I couple them with this Laplace matrix, L0 because are nodes, L1 because are links. Now there is a minus because here I use the opposite definition of Laplace matrix, but never mind. And now you have to assume again the existence of a homogeneous equilibrium, but now this is not straightforward. So why for the network we got this fact that the homogeneous equilibrium is a solution for the whole system because of this equation? In the case of simplicial complexes, it's not longer true. Only some simplicial complexes are such that once you do the product, B times constant is equal to 0, AB1 times transpose times constant equal to 0. So you cannot have a Turing pattern on any simplicial complex. There are some topological constraints. In case of networks, this means that all the nodes should have degree even. should have an Eulerian network. So here is an example. This is a very simple network where I have all the nodes with the degree 4 or 2. I run the simulation. This is the quantity that evolve on nodes. This is the quantity that evolve on the links. And you can see that, okay, I didn't do the math, but here you can see that you have evolution of something which is patchy, so it depends on the position. And what is important is now I have inhibitor. So something is not possible on network, is it possible on simplicial complexes? Because now I have, if in some sense I remove the support, I only consider the species, they will go to 0 or to the equilibrium because they are inhibitor. But the presence of the simplicial complex allows to have this emerging of structure. Okay, so with this, a bunch of papers that I wrote with some collaborators about Turing pattern, another set of papers I can share with you if you want, and I thank you for your attention.
Thank you very much, Theo. Questions? Well, let's start here. We have to go somewhere.
Well, I'm trying to picture, so the diffusion in the case of the links was easy to understand. There was just some discrete form of the spatial diffusion. I was trying to understand in the case of simplicial complex, so is it really like the vorticity, so the presence of a circular current in a triangle, is that a geometrical interpretation of the diffusion there?
Yeah, I prefer to call diffusion-like because it's not real diffusion, it's not fake. But the idea is that, for instance, suppose that you have two triangles in that way. Okay, so what happened here, so maybe this circulated the way, so this will interact with this link that also will interact with the other. And so the interaction is mediated via something. So as in the case of nodes, what happens here is mediated by the existence of a link that join to it. So it's the same idea mathematically. So these two triangles do interact because they share something. If I had something like this, those two will not interact because you need something dimension -1. The nodes is dimension -2 with respect to the triangle. So in this case, there will be no diffusion or interaction among the triangles, while here you will have interactions. But of course, physically, I cannot explain what does it mean.
Can you hear me? Yeah. No, it's more or less the same question, but because I don't see really what, in this case, what is simplicial complex is, what is the role of simplicial complex in this process? What is the physical meaning of putting this in a simplicial complex? Yeah. For me, the process itself is not clear. Of course, mathematically you can do, but
okay.
I am interested also in the physics of that.
Yeah, of course. So I discussed it with some colleagues from physics in Florence, and they told me, so I believe because I don't know it all, that in some condensed matter problem where you have arrays of atoms, then you can have, so the node is the atoms, so this is the node of simplex, and then you have a connection among atoms that are the links, and in this case they are squares, so but it's the cell complex is the same. Then you can have some action of the square that depends on the links and on the nodes. Some sense in some models of maybe it's the wave function, I don't know how they interact exactly, if this is local or not, but there can be some interaction mediated by the presence of a link or a phase through different object different dimension.
Yeah, I'm sorry. And just a follow-up question is, because you didn't mention that, but you said that you have done this also on hypergraph.
Yeah.
That for me are more general structures that simplicial complex that are very peculiar ones. So what are the results for hypergraphs? If you can briefly.
Yeah. So I skipped that part. So the point of a simplicial complex is that you have a topological structure with these matrices and so on. But there is the point that if you have a triangle, all the pairwise interactions should exist. If you have a tetrahedron, so a pyramid, all the faces, all the three-body interactions should exist, all the links should exist. So this is maybe not true. So that's why people use a hypergraph. And in the hypergraph, here I just show some result that we got by using this an hypergraph is just a set of points that you put together in some blob, if you want, some hyperedge. And then you can have hyperedges of size 1, 2, 3, 4, whatever you want. But there is no any constraint of being part of the 3 hyperedge or 4 hyperedge to be also part of the smaller one. So this is really a much more freedom. But this freedom comes to the cost that you don't have the same algebraic structure that for the simplicial complex. And then in this case, what we did, we used a kind of what we call hyperedge mean field. So all the nodes inside the same hyperedge are more or less similar, and the interaction, so if I look at the interaction of this point with those 2 points, I will say I take 1 or 2 at random, but then I multiply this interaction by the size of the hyperedge. So this is some sort of the group interaction push or even reduce the strength because of the size of the group to which you belong to. And so in this way, again, we got some sort of projection on some network where the projection, the links weight according to this kind of weight that I put on the size of the hyperedges. Thank you.
Excuse me, he had asked before. Oh, you first.
Yeah, so I have one question. So what new results you get if you consider simplicial complex instead of pairwise interactions?
Okay, so
which is not possible if you only consider pairwise in terms of simplicial. As
yeah.
hypergraph, of course, has something extra.
Okay, so in the example of simplicial is what I show you. This is inhibitor. It's just impossible on networks. So here, if you take this very simple simplicial complex, so it's a network after all, because there are no triangles here. Yeah, I have both inhibitor, but one species live on the links, one species live on the nodes. They communicate once the links interact with so the links enters in the node, but that's all. And then each one lives in its own space in some sense. In this case, you can have this kind of...
if you take pairwise also and then take one inhibitor on the link and one on the node, they are also...
yeah, so I think it's not so easy to transport this example in the pairwise, because in the pairwise, or you are thinking of co-evolving network. No. Yeah, but in the network, normally you don't write the equation for the evolution of the link. If you do, it's exactly the framework of simplicial complexes. So if you take a network and you put one variable on a node and one variable on the link, and you write an equation for the node, an equation for a link, that's all. But it's a simplicial complex. It's just you name it the network.
Just one thing to complete that. So what you are telling me is that since you're not looking at the dynamics of the link, you're not putting the dynamics of the link, would it mean that this type of description, let's say the simplicials, will not be able to be applied to the system of neurons in which you consider the dynamics of a neurotransmitter?
This could be a possibility. So you can have the model of the node that is the neuron, then you can have dynamics across the axon.
Yes.
In this case, I think that the phase can have interaction because a current flowing the axon induces a magnetic field. And so if I put a magnetic field on the triangles, then can be a feedback on the axon.
Yeah, of course.
Okay, but
William wanted to ask a question. Oh, you also?
Yeah.
So,
Okay, about the temporal network case, your effective network approximation, is it still valid when the times at which the network switch the connections, if those times are stochastic, is this approximation still valid?
Yeah, so is it fast enough? Yes. So in the appendix of this paper, we show that you can have a random, so you have a reservoir of networks, and you pick it random once, and you put after that. So you have a discrete time evolution, but each time with the fixed windows. And then if, so you need that the average exists, so the Laplace averages exist. So this means how random is the sequence of network. But in this case, there are some Sturmian world where you can have this.
Okay, but those times need to be fixed.
The data, yeah.
If they are now random variables.
Ah, okay, so I thought the random is the network.
No, the times are random.
I didn't think about it, so, but I think if you can prove that there exists the average of this function, once the so you have several Laplace matrices, random, because they stay for different times. If you can prove that some average of this function, these matrices exist, then you can invoke the average time theory. This is a dynamical system theory that tells you if I go fast enough, I will be close to the average system, and then if the average is unstable, I will also be unstable.
Okay.
But you have to prove the existence of this average.
Okay, thank you.
Thank you.
Thanks. So I have the question regarding the diffusion coefficient, because in the continuum, your diffusion coefficient will have a dimension of area over t, right? So I can get the diffusion time by dividing my diffusion coefficient, multiplying the inverse of my diffusion coefficient by some measure of the area that will be the dimension of my plate or whatever stuff. But here, your diffusion coefficient in the graph will be only have 1 over t, dimensions of 1 over t.
Yeah, if I use the adjacency matrix being 1 or 0, I agree with you. But you can have a weighted adjacency matrix.
But suppose that you have your simple adjacency matrix. My question was, how do I estimate the diffusion time in a graph? What is I know that must be inverse to the diffusion coefficient. That is obvious because dimensional content. But what is the factor that I put? Is the number of nodes? It's some kind of degree, the degree of the graph? What is the
So the way that you get this kind of L matrix is really the same construction that you are doing for the Fick law. So you assume that there is a current. You look for the time evolution of the current, and then you check for the conservation of, so if you remove the reaction, I mean, and you look for the conservation of the mass. It's the same equation that you can write for the network. But of course, there is no dimension, spatial dimension.
But so if I tell you what is the diffusion time, you will tell me that is the inverse of the diffusion constant in this case, without any factor.
Yeah, without any factor.
Okay. And the other small question is, so at the end, you mentioned that there was a role played by the faces and the edges in the simplicial. So the boundary operator has some kind of interpretation in terms of this dynamic. So you have some kind of construct, I don't know, a cohomology of this kind of stuff.
It's exactly.
Cool.
I work in the cohomology group. Yeah. So the B matrices are the analogous of the derivative gradient and in some sense rotational. If you use a discrete geometry. Yeah, exactly the same. Yeah.
Thanks.
Any other question?
Yeah, in the middle.
There.
Okay, so I'm trying to reconcile two things that you said in my head. Is first, when you first presented simplicial complexes, if I understood correctly, the idea was the quantities, they live on the vertices, and if you have an edge, then two vertices interact. If you have a face, then there are three vertices that are interacting in a kind of three-body interaction or a term with a product of three quantities, things like that, and so on. But later, you said that the quantities would live on the edges, the quantities would live on the faces, and the edges would interact through common vertices, the faces would interact through common edges, and I don't see how those two relate.
So sorry for the misunderstanding. There are two different approaches. So the first one is that use the simplicial complex, so the fact that you interact pairwise, 3 bodies, 4 bodies, and so on, by using, as you say, a function that depends on the number of the many bodies interaction. So here the variables are only on the nodes. And so I have some reaction on the nodes, but I interact with 1 node, so there is a 1 pairwise interaction. I interact with 3 nodes, and I have some function h that depends on 3 variables and so on. This is the one framework, but the dynamics is still on the nodes. But then I say, okay, one can try to go farther in some sense and assume that, okay, now also the links carry some variables. Also the faces carry some variables. And then you can try to understand how the variables evolving on the face interact with the links, interact with the nodes, and vice versa. How two faces do interact because they share common links. So there are two different approaches in some sense. But the same underlying structure is the same. It's a simplicial complex.
I mean, the geometrical structure is the same, but if I understood correctly, in this latter approach, the interactions are two-body only, because you have, for example, a face can interact with another face only if it has a common edge with it, but it cannot interact with two other faces at the same time.
No, because one face has three edges. So if you
Right.
take a tetrahedron, so a tetrahedron interact with 4 triangles.
Yes, but it's not a. It's
So-
it's three. In a tetrahedron, you have three three interactions with a single face, but not one 4-face interaction. You see what I mean?
1, 4, 5. So this is not the case of tetrahedron, but if it was the same of tetrahedron, so here you have the matrix B3 that tells you if I take some tetrahedron, it depends on the variables that are living on the 4 faces at the same time sometimes. So it's not a pairwise interaction of one face with tetrahedron, other face with tetrahedron. Is the tetrahedron, the evolution of the tetrahedron variable will depend on the 4 faces.
Okay,
Maybe we can discuss later if you want.
thank you.
Okay. Any other question? Who?
It's over there.
There.
So you're talking about simplicial complexes, and I immediately think about homology theory in algebraic topology. So I was thinking that maybe some topological invariant could appear in these systems, and maybe you could extract some information about the patterns using these invariants. Do you have any information about that, like that's ever used? Or
you are right. So if you have some symmetry of the simplex, you can reread the symmetries on the topology. On the dynamics. So if also this is also true in the case of network. If the nodes are you can permute the nodes, the network is the same, then this means that the dynamics of these 3 nodes will be the same or very similar in some sense. The same can be done, of course, here. Yes, true. So the symmetries on the structure can be seen in the dynamics.
Do you gain like any extra information about your system when you do this kinds of like calculations, or
What do you
no?
mean extra?
I mean, like I think you can actually evaluate like a topological invariant in your system using this kind of like constructions. So I was thinking that maybe if you run some simulation that kind of extracts your topological invariants from your system, you gain some information about some
you mean
symmetry
some
that you
inverse
didn't think
problem. So I look for the dynamics, I try to understand the structure.
Yeah, I think so. Yeah.
I'm not sure I've been done, but I think yes, because on network you can do it. So again, except for symmetries, because you cannot see. So if you take a random walk of network, you can reconstruct the network. So not the whole network, you can reconstruct the degrees distribution, for instance. So maybe here you can do some diffusion process, only diffusion, not reaction on simplicial complex, and maybe reconstruct some hyper-degree distribution. Yeah, maybe, why not? I'm sure. Yeah.
Thank you.
Thank you.
Okay. Any more? All right. Well, thank you very much,
Thank you very much.
Theo, and remember, yes, remember that now we have the group picture right outside.